We quickly give a recap because you need to learn how to look at these circuits. These circuits are very similar. It's all about how to find the terminology and comparison with the analog case. We have a buffer, analog buffer. So we replaced it by a flip around, and these are all op-amps, small signal analysis. I show it this way because I just want to keep small space here. So S1, S3, and this is capacitor C. So eventually it was just converting that continuous time to discrete time. This is continuous time converted to discrete time, right? So instead of continuously applying V in, we store value of V in at some eventually tracking period or capacitor C, and then we put C around op-amp, that's it, flip around. So that was already there. For example, if I want to show that case, for example, switch S3 will be closed, and we have it, and this is discrete time. Then we went and we had eventually few things that we should always remember. One was sequence of switching. Which switch will turn on first? And sequence of turning on and turning off in general. So this was very important. Second thing was speed, for which we developed the models. And then we had precision, which depends on the limited gain of op-amp for now, due to limited. So these three always should come for all switch capacitor circuits. Precision also includes effect of charge injection, and that's why as much as possible we use bottom plate switching configurations to avoid effect of charge injection. It is also sometimes called driven plate. We are driving the plate either with V in or we connect it to the op-amp output. So therefore, these are the ways that we are always trying to do to avoid the charge injection effect, and this already we have discussed. So now going with amplifiers, again we go with the corresponding amplifier in analog domain, and because we want to be absolutely a capacitive based, so we go even with capacitive based continuous time amplifier. Of course, this is not valid for DC in general, in continuous time. In discrete time, it's a different thing. So now we want to make a counterpart of this case. So it's actually very similar to this case. So still this capacitor C2 will be switched so it switches to. In this case, we were storing V in on the capacitor C. We were also putting capacitor C in the feedback pad. But now here, we have already C2 in the feedback pad. We don't remove it. We just connect it and disconnect it around the feedback by bypassing it with switch S2 or keeping S2 open, and C2 will be in the feedback. What we will do, and keep in mind all these ground symbols are AC ground, not DC ground. Okay. So in this case, effectively we want to switch the capacitor, C1. Now, see, one way of course would be like, you know, the way we had in the sampling. Suppose if I put a switch, C1, and this is Vin. So I sample the Vin on C1, and then in the next phase, I will connect it, say, to the input of the circuit, C2. So what is the concept over here? One thing we have to be very careful. So we are charging this capacitor to some charge, say Q, which is coming from Vin. So when we connect it to the virtual ground, this charge will go to 0. And charge will get transferred to this capacitor, right? So this will be Q now. Is that correct? So therefore, output voltage now will be minus Q upon C2. But Q actually was C1V. So therefore, effectively, we have an amplifier with a gain of C1 upon C2, right? Of course, we know that this configuration has the problem of charge injection, right? This was the first, in fact, sampling configuration that we had. Okay. So here, a little will change this configuration. The main reason is because we know that there is charge injection problem, but concept is similar. Therefore, we move to this configuration. So it's a similar, very similar. Switching at the input only is different. S2. Okay. So I want to avoid that. So this is the configuration. See, eventually if I want to avoid that, I have to try to drive the plate of capacitor, which is right now grounded. So therefore, instead of going with that, I keep the capacitor horizontal. In fact, as soon as you make it horizontal, you are driving both of them. And put the switch over here, Vin, say switch S1, this was S2, and this is capacitor C1. Still, I am charging C1, same as before with Vin, but the right plate terminal is connected to virtual ground rather than actual ground. So that now, when I want to discharge the capacitor, I will make this side ground. Now charge injection problem goes away. Fine. So therefore, what is the cost? Only I need to add one more switch, which is absolutely fine. Now this left plate also is switching. If I keep vertical, it becomes bottom plate switching, or we can call it left plate switching. It's fine. So then now we have the configuration. So this switch say S3. Now let's look at the output here. So we are storing the charge. So let's say this is Q. Again, same thing. Is C1 Vin when switch S1 is closed. So eventually switch S2 and S1 should be closed at the same time. And S3 is open, is closed in the amplification phase. Instead of track and hold phase for unity gain buffer, here the hold phase actually also is amplification. So we have track, which is also called sampling, and hold, which is also with amplification. Now, see, we have eventually amplification come hold phase for a discrete time amplifier. So now this Q is discharged in the capacitor C2, or eventually. So now C2 charge becomes Q, and Q goes to 0. When I open S1 and S2 and I close S3. Now what would be the V out? So V out will be Q upon C2, and Q is C1 V1, so therefore you will have C1 upon C2 multiplied by V. This is actually, say for example, we have to be careful. This is actually V out N. So it could be N minus 1, I told you, depending on the phases, or otherwise you can. On the right side is discrete time, just like sampling switches. On the left, this V in could be coming from another discrete time circuit, or could be coming right away from a continuous time input. So on the right, therefore, we start using N. What is the difference between these two configurations? One is, of course, architecture at the input, which allows us to have the bottom plate switching or left plate switching here, and therefore charge injection problem goes away. So this is for solving charge injection problem. Due to S1. Do you see any other difference in any way, in any aspect? One extra switch, of course. This is non-inverting. This is inverting. That's another difference. That's very interesting. Even though the initial analog version also is done in inverting amplifier, but by this method, which actually we are changing the polarity of charge, which is transferred to C2, we can make actually a non-inverting amplifier. That is, anyway, is the next difference. So non-idealities are same as before. Therefore, switch sequence matters a lot. Okay. Let's say, for example, S2 is open, S3 open. We are talking about this state. And S1 closed. This is the tracking phase. You tell me, what would be the sequence if I want to go from track to amplification? Right now, there is no difference between them. It's just a state, current state. So this is amplification phase. Okay, so which one should? So two of them are open, one is closed, S1.
The tracking stage, shouldn't S2 be closed?
Oh, yes, yes, you are right. Sorry, S2 is closed, yes, buffer. It should be unity gain feedback. C2 will be discharged completely and C1 will be, yes, thank you. S2 is closed, fine. So you tell me that now, what should be the sequence? Those which are closed should be open, the one which is open should be closed. Which one should turn off first or turn on first? Can I, for example, turn on S3 first? Exactly. So you have been shorted to ground. That's for sure. You cannot do that. So fine, S3 comes later. What about S1 and S2? Which one should be closed first? Sorry, opened first? S1 or S2? Yes, yes, of course, that can go away still with S3 later. Yeah, see, problem is that if we open that, charge injection will happen. And we expect that with bottom plate switching to go away, right? The problem is that because S2 is closed, so this is still as a buffer, and this is a virtual ground. C1 doesn't recognize it is because of the charge injection. Still, it will see it as VE. Means the circuit cannot recognize the two cases. Therefore, we have to open the C2. Therefore, S2. So therefore, S2 will be opened first. Now here we have order. In fact, this is now 1. Then we will open S1. Another point is that when we open this switch, this node B becomes high impedance. If switch is closed, node B is low impedance. Remember, for avoiding charge injection problem and compensating automatically, we needed a high impedance node. Therefore, here, now B eventually moves from low impedance condition to high impedance. This is very important in all these orders of switching. When you have this high impedance in the steady state, of course, now you can open the switch as well. And then we go with closing S3. So this is. So first we will convert this node B, which virtual ground, which is a very important node at the input of op-amp, to high impedance mode. Open S1, close S3. And exactly this analysis in a generic manner, I have done it before to show that how charge injection problem is solved. Eventually what will happen is that the charge is injected, but as soon as you connect to ground, charge again will be discharged. Because if it is closed, this node is connected to the output of the op-amp. So output of op-amp with a unity gain feedback around that will give you a low output impedance, right? So therefore, it is exactly same as sampling phase. So the charge which is coming from S1 will stay on C1 as a part of VE, right? So therefore, it becomes a part of VE. But when we make this high impedance, now this input capacitance will show up. Even if there is no capacitance, so C2 will be there. So therefore, the charge which is injected will go to C2. When we and these charge values are same, say C in 0. As soon as you connect it to 0, the same charge will get discharged on both. When this is shorted, C2 will not receive any charge. And the entire charge will be absorbed by the output of op-amp, which is low impedance. Therefore, charge only is on C1. And therefore, it can't get discharged. The whole charge will get transferred to C2 in the amplification phase, including the error due to charge injection. Advantage of this is that now we have a capacitively connected node. So therefore, any charge which comes after the S2 is open on C1, similar charge goes on C2, and you see that it is also exactly opposite to the direction. When you discharge, this charge will go to ground, this also will go to ground. What remains is only effect of V in when switch S1 was closed. That's why it works very well for reducing effect of charge injection of C1. Okay, so therefore only S3 is closed in this case. Therefore, naturally, when you want to go to the tracking phase again, first you will open S3. You close S2 and then you close S3. Yeah, that's it. So therefore, effectively, if you go with this sequence, so S3 becomes open. S2 is closed, and then you close S1. So that is the order for the two states when we move from one state to another state. So this is a discrete time amplifier now, and it doesn't have charge injection problem. So eventually we will not cover circuits which have charge injection problem. We go with only bottom plate sampling or bottom plate driven configurations. It's bottom plate, sorry, switching. Bottom plate switching, I think, is a better name. So eventually we are switching it, or we are driven. We can say we can drive with ground, but yeah, it's better to call it switching. It's a better name. So we are switching it to ground. It's not permanently connected to ground, like that, this configuration. So this configuration, therefore, we will not follow. Okay? Though theoretically works, but technically is not used. Okay, so practically is not used. So regarding the precision and speed, maybe I can write here itself without removing the configuration. So it's actually very similar. Because if you look at this configuration, the configuration we had during the hold phase, I just showed the configuration with respect to capacitors. That was the generic case, right? Adding a CL, adding C in. So, and we analyzed it in the class. In fact, I also derived it in two ways for you. And one way was actually the very generic way. Do you remember this was the configuration we considered for the speed? Because the purpose was to find the poles of the circuit. Now look at this circuit. I draw it during amplification without showing switches. Are they same? Configuration wise. The two circuits which are shown in yellow color on the extreme left and extreme right of the board. Are they same or different? Fine. But as far as parametric consideration is taken into account, it is not different, because if I just write, say, a C equivalent equal to C1 plus C in, the two are same. One op-amp, one capacitance from negative terminal to ground, one capacitance at the output, again between output and ground, and one feedback capacitor. So therefore, both of them show same speed, parametric wise. But value wise they are different, yes, because now instead of C in, we have C in plus C1. So therefore, we just replace what we had before by adding the C1 to C in. So therefore, we don't need to do the recalculation. And do you remember it was a function of GM? C in, C2, CL, tau. So therefore, we write again same thing. Therefore, tau amplification for discrete time amplifier will be equal to, like it was 1 upon GM. I want to write in the same form we had for the okay, I wrote it the other way around. That's okay. So 1 upon Gm. Okay, I wrote it reverse because the capacitors came in the denominator. Be careful, this is tau. I have written tau inverse for you in the previous case, but doesn't matter. So tau eventually is 1 upon Gm. Now here we had the effect of capacitors. And now what I will do, I will just add the effect of the Cin as C equivalent. So it is C equivalent plus Cl into 1 plus. So do you remember we had Cin upon C2, which was the feedback capacitor. Now we have C equivalent upon C2. And upon, yeah, that's it. It is already divided. Little shifting. Okay. So what is C equivalent? We write it again over here so that we can, it's eventually C1 plus Cin. So actually I write it directly in the expression because one of these capacitors is not parasitic capacitor, it's the actual capacitor. So therefore it is C1 plus Cin plus Cl multiplied by 1 plus C1 plus Cin upon C2. And if I want to take this C1 out, so I can, and show the parasitic effect separately, so it is 1 upon Gm multiplied by, so see, this is C1 plus C1 upon C2. So therefore I will write 1 plus C1 upon C2. This term I'm taking out, and then I have Cin plus Cl
It is C1 upon C2 times Cn.
1 plus, yes, multiplied by Cl, right? This is what you say. This part is left, yeah. Cl, right?
That is already over there.
Oh,
But you have considered it on the right.
see, I 1 upon Gm.
That is
This is C1 plus Cin. This is C1 plus Cin upon C2 plus 1 into Cl.
yes, so afterwards.
Afterwards. Oh, I am writing this here. I have not finished it. So now I am taking out C1 upon C2 multiplied by Cl. I think this is what you said, right? This part. Right. Okay, so Cl, because this is not coming from Ce, but it's coming from ratio of C1 upon C2. And then I'm thinking, should I keep it as it is? Actually, let's keep it as it is. It is, in my opinion, actually it is better. What's the problem if you keep it as it is? Yeah, because what it says is that C1 plus Cin upon C2 is showing effect of Cin. If Cin is 0, we have only 1 plus C1 upon C2 multiplied by Cl. Now this will add to the multiplication factor of Cl. And this is also extra parasitic capacitor. Yeah, actually this is better. Let's keep it as it is. This nicely shows the effects. Effect of Cin and effect of Cl. In the previous case, this C equivalent was only Cin. Yeah, it was Cin plus Cl into 1 plus Cin upon C1. Cin plus Cl multiplied by 1 plus Cin upon C1, which is C2 over here, yes. So now we are just adding to it's the same. So eventually, it was Cin upon C2, and this was Cin, so I will replace here. So that is enough. That shows the effect of both Cl and Cin. Okay, so therefore, see, we don't need really to derive values. So, or write the equations again. So we are just by the analogy with the two configurations, we go with the speed. So eventually at the end of the day, it's the same thing. C in should not be very high. CL contributes to the speed, which is expected, right? And now finally, GM, which shows the trade-off between the power and the speed. Okay, so then there was also precision. So let me just talk about precision as well. And then we will finish this at least one configuration of amplifiers. We are almost done. For the precision also, I can write a final expression. Actually, interestingly, if you calculate, it will be same. In fact, relative gain error will be similar to what we had before for the flip around discrete buffer, discrete time buffer. Relative gain error still in this case will be same, which is eventually 1 plus C1 upon C2 plus Cin upon C2 upon A, gain of amplifier, op-amp, open loop gain of op-amp. This is relative error, gain error. So this is the effect of Cin on the precision, and this is the effect of the open loop gain of op-amp on the precision. And also it's very clear that if you want to increase the gain means that we want to increase ratio of C1 upon C2. The effect will be increased relative gain error. And that is valid even for the continuous time. If you increase the closed loop gain with an op-amp, relative gain error increases. Okay, good. So we also showed one amplifier which also got converted to non-inverting, though it is looking like inverting, by using the bottom plate switching. And we have also one buffer. And now you can look at the circuit which was in the Razavi's paper on the article, on the pipeline ADC. There only I give you this. He has given also the same thing in this chapter. In that article also it is used. In fact, do you remember in MDAC we need multiply by 2 or multiply by 4, right? And you need to do it in discrete time. So this multiply by 2 can be done by a technique like this, right? Now there is another technique which is actually used, and it is still a switch capacitor discrete time amplifier, but by increasing the number of switches and charging C2 also to be in, it actually provides gain of 2 using same capacitors. Therefore, it will save the area, and you don't need to really use, because here you have to make C1 to be 2 times of C2. So you can still have C1 and C2, add extra switches to charge also C2. Like combine these two configurations, flip around and discrete time. You will get a new discrete time amplifier when both capacitors are switching. And the whole idea behind that is this simple concept. If you charge a capacitor C2, say this is V out, by a charge Q, and the other capacitor also with the opposite charge Q, right? And then discharge it here. Say both of them also are same capacitors. C1 equal to C, C2 equal to C, just a concept. Suppose I just put a switch that is actually is not a switch this way. So eventually it's a virtual ground. Suppose this is virtual ground. So if it is virtual ground, so therefore I show connections. Charge on this capacitor will be discharged in C2, but it will add to the charge in C2, right? So charge on the capacitor C2 now becomes 2C, 2Q. That means by just choosing the polarity, you can get double of charge. That means by the same capacitors, you get gain of 2. That's the advantage of the switch capacitor circuits. So therefore, we would be able eventually to make a combination of the flip around, because in flip around we charge C, and then we put it in the feedback. So we charge C, we put it in the feedback, and then we use this discharging C1 in C2. So therefore, you will get actually gain of 2. And this is one of the common circuits in MDAC with gain 2. Because then you are matching the two capacitors very well. C1 and C2 are exactly same. So it is better to achieve a gain of exactly 2, because it is very important in MDAC gain. Otherwise, effect of MDAC gain change will get transferred to the next stage and we will get error. Right? Okay. So that's fine. So effectively, we have almost covered the entire chapter. There is one extra section on the switch capacitor integrators. So the integrator is same as this configuration, and this grid time similar to this configuration, only what you do is that don't switch C2. Let it just accumulate the charge over time, it's integrator. Like one resistor here, which is now replaced with a switch cap, and here you have a capacitor. So it's very simple. Now, in fact, that part is very simple and simpler than what we have discussed till now. So please read that part as well. Switch capacitor common mode feedback is extra reading, which is a small section at the end. It's only for interested students. It's we don't have time to include it in this course. So eventually by this we have completed the switch capacitor section.